In today's video, we're going to do mass spectrometry and go through all the techniques that you need to get all the exam questions right. Okay, so first of all, a mass spectrometer can tell the individual masses of all of the parts of a mixture, and one specific mixture is, for example, when you're doing relative atomic mass. So to calculate relative atomic mass, you need the mass of all the isotopes. So here's an example of a mass spectrum where you've got all of the masses of the different isotopes. And you notice it has a relative abundance on the left-hand side. Okay, and everything is set to, where it should be set to around 100. Okay, so we'll talk about that later on anyway. Now the mass to charge ratio is a mass to a charge of 1+, which means mass to a ratio of mass to a charge of 1 is literally just the same number. So basically you can count mass to charge ratio as mass of the thing. So basically this is the mass of the isotope, mass of the isotope, mass of the isotope. Okay, so let's have a quick talk about what the machine actually is. It comes out with something like that, and we'll go through many examples of that as well as we go through the video. But let's talk about the actual machine itself. So first of all, we start with there's a detector at the end here, and there's a big long tube. Now, first of all, we have to put it in, so the sample enters here. Okay, and this is usually an injection of a small amount of substance, like tiny amounts, like nanograms, micrograms, tiny amounts of substance. Now, from that point, the heat vaporizes the sample. So it's vaporized, okay, and then it gets hit by an electron beam, okay? So when it gets hit about the electron beam, that is like, imagine if someone's being shot with a gun, okay? So if someone's shot with a gun, you get the entry wound, but you get the exit wound. And when you go the exit wound, what they don't show you in movies is that the exit wound is very large. So if you shoot somebody in the front here, then the back of the head, a larger hole in the back of the head will come out, okay? So basically, if you shoot someone, there'll be pieces of that person going away. And it's the same thing here. If we shoot electrons at our sample, that sample is going to have electrons taken away from it, because the electrons that are being fired with the electron beam will take electrons away with them. So that turns this sample into a positive sample. Okay, and that positive sample goes into the machine, as you can see here. So the gas goes in, remember it's vaporized, okay, it gets hit with electrons from the electron gun, turns into a positive ion, and there's 2 electrons at the end. You can see here, one from the gun and one from the molecule. And we call this M+, the molecular ion, okay, because an electron has no mass. Because an electron has no mass, well, a very tiny mass, then the M+ is equal to the mass of the entire molecule. Okay, so if we're going to analyze a molecule in a mass spectrometer, this value here, this M+ value will be the molecular mass of the substance. And that's arguably the most important thing you need to know. The M+ is the molecular mass of the substance. Right, okay, after this point, it has been ionized, okay, and then it's going to get put through an accelerating part of the mass spectrometer. So the ions are going to be accelerated. They get accelerated to the same kinetic energy, so the same speed. All of them are exactly the same speed at this point, because we've accelerated them up to a speed that is consistent across all of the parts in this mixture. Okay, so they're all going the same speed, and then they get put through a really strong magnet. Okay. Now, the magnetic field deflects the lightest ions the most, okay? And that means you get different paths. So you can see different paths here, okay? And those different paths take different amounts of time, okay? So let's just get rid of that equation. They take little bits of longer bits of time. So if it's a longer path, it will take a longer bit of time. If it's a shorter path, it will take a shorter piece of time. Now, these are called time-of-flight mass spectrometers, as in you analyze the time of the flight. So now some clever maths can then turn that time of the flight into a mass, because the mass, the time of flight depends on the mass. Remember, it deflects the lightest ions the most. Okay, and you can rearrange the kinetic energy equation if you want, with kinetic energy as a constant, and you'll find that the mass affects the speed or the velocity. So basically, if the mass affects the speed or the velocity, that means we can convert that with some clever maths, which you don't need to know, into the mass of the fragment or the ion that's going through. Now, important thing is we only detect the positive ions. So we only detect the positive ions. That is it. We don't detect the neutral ones. Okay? They just hit the detector and nothing is detected. But we do detect the positive ones. And things can break in different ways. So for example, this molecular ion can break up. And that breaking up we call fragment or fragmentation. And the A plus here can have a B fragment, which is neutral. Or we can do it the other way around. We can say the A is going to be neutral and the B plus is going to be positive. Okay, so that means because there's billions and billions and billions and billions of molecules in there, that you'll get fragments of every single type of part of this molecule. You'll get every single part. Because one molecule might split in this way and another one might split in this way, and then that B plus or that A will get ionized again and then and fragment again, and you end up getting a really complex spectrum, which we'll show you later on in the video. So remember, only positive fragments are detected, and each time a molecule fragments, it produces a neutral and a positive fragment, but only the positive fragment is detected. Okay, so let's have a look at a mass spectrum. Okay, so here's a mass spectrum. Okay, and this looks a bit different to the one we showed you at the start. So first of all, the one with the highest intensity, as in the number, that's the number of counts it hits the detector on. So how many of those molecules have hit the detector? And it will, imagine it counting 1, 2, 3, how many times it hits there. And the one that has the most counts on that detector will be set to 100. And you can see it's set to 100 here. And then everything else is relative from that. Now this has just been put through the mass spectrometer, and it is a hydrocarbon. Okay, so it is some form of hydrocarbon. Now, if I look through here, you can see there's a peak towards the right. Okay, and that is my M+, the one most to the right. But then this little one right by it is usually an isotope peak, and we'll talk about that more as we go through. But remember, everything is made up of different isotopes. Okay, so a carbon has about 1% carbon-13. That means there'll be a peak here that has a carbon in that has a carbon-13, which means that tiny little thing is probably just a carbon-13 peak. So if you see the peak furthest to the right is usually the molecular ion. If you see a tiny little one just right after it, that is the isotope peak, and you can ignore it. Okay, because that is the M+. Then this bit here is all the fragments. So this is all the fragments, and we call that the fragmentation pattern. Okay, so, and you can tell from the fragmentation pattern what the substance is. Now, the fragmentation pattern in your course, you just have to look at it and go, oh, okay, what's one of these peaks usually? And sometimes you don't even have to. The most important thing is that you recognize where this M+ is. Okay, and you quote this M+, and we'll talk about that later. Now, if that is the case, the molecular ion, like I said, is furthest to the right. It's the peak with the highest molecular mass, and you can disregard that isotope peak. Okay, so that's really, really important. The one thing you must do the entire time is quote that, and we'll quote that lots as we go through different mass spectrums. Okay, so there you can see the molecular ion peak, okay, and the little blue, you can barely see it there, but I've just made that blue down there. That's the isotope peak. Okay, the next one is this orange one here. And you can see this orange one is known as the base peak. There used to be a lot of questions on this, but not so much, but you still need to know that it's there. That's the base peak, and that is the peak set to 100%. Okay, so that is the most abundant peak. Okay, so the most abundant peak that is set to 100%. Now the other thing is it must be the most stable ion because it gets through to the detector the most and it doesn't break up. The one that doesn't break up must be the most stable. So therefore, this is the most stable peak and the most stable fragment of everything in this mass spectrum, the one that's set to 100%, the one that hits the detector the most. Okay, let's actually look at what this thing is then, shall we? All right, so this is heptane. Oh, 1, 2, 3, 4, 5, 6, 7. Heptane. Okay, so I'd like you to stop the video And I'd like you to look at this mass spectrum, and I'd like you then to tell me what the base peak is and what the molecular ion is. So what you need to look at is just look at chopping these bonds up. So don't worry about the hydrogens that are coming off here. Just chop the bonds up, and you'll find that this number here, okay, this one here, which is 43, I'll tell you that's 43, is this chopped up slightly. So stop the video right now and try and do it. So hopefully you've looked at all the peaks you might get, but again, I challenged you a little bit there, so if you didn't get it, don't worry, and you just carried on. That's absolutely fine. So let's look at the mass spectrum. So first of all, we're going to look at the molecular ion peak. The molecular ion peak is down here. Remember, this is an isotope peak, this little one here. Okay, and then this is our molecular ion peak, and that is set to 100. Okay, so just look, there's your 100. So that is our M+. So I'm going to write M+ equals 100. Okay, and if I want to, I can put M/Z after it if I want, but that is our molecular ion peak. And that just basically means that it's heptane. So heptane is C7H. So C7, let's get rid of that. That's C7H. Hopefully you're working it out. Okay, 16. Because this is N, and this is 2N plus 2. Okay, and then you can just put that, and that's your M+ fragment. Okay, so that will get you a mark straight away. Now, all we do now is we look at this and we go, right, okay, what would happen if we broke it there? And I only worry about breaking carbon-carbon bonds. Don't worry about anything else, not at this stage. Don't worry about anything else. So if you look here, that would be a CH3 on that side, and that would be 1, 2, 3, 4, 5, 6. So 6 carbons on that side. So I've drawn those two there. Okay, so there's CH3. Notice the plus, really important. Okay, the plus, really important. And I've drawn it all out. So it's big and a bit annoying, but you know, I've drawn that all out. And notice the 85 and the 15 add up to 100. Okay, so I know I'm right. Okay, but instead of doing that, let's just see if I can get rid of this. That's good. Okay, and imagine I've got another molecule of this, but this one, it broke there. That would have 2 carbons there. Well, there's that one, 2 carbons. Remember, we're counting all the hydrogens, right? And notice I can do it in shorthand. I don't have to do it like this. I can just write it out as C2H5. They don't care about doing it in detailed ways in mass spec. You can just count the carbons, count the hydrogens, and put them there. But still, on this one, I've written them all out. And notice 71 plus 29 is 100 again. So that's the 2 fragments if I broke it there. If I get rid of that, okay, so I've done this one and then go for that one. There's 3 carbons, there's 3 carbons, and then there's 4 carbons, and then there's 4 carbons, okay? So then that adds up, 43 plus 57 is 100 again. So if I then carried on and broke here, I'm going to get 4 carbons again and 3, so it's this one again, and if I broke here, it would be this one again, this one again. So I would expect to see all of these peaks. Now, if that is the case, okay, then I should see them on this mass spectrum. So basically 15, do I see 15? Well, 15 is this one here. Do I see 85? Well, 85 is that one there. Do I see 29? Well, 29 is hidden in those ones there. 71? 71 is this one here. Okay, 43, it's this one here. And 57 is that one there. So I do see all of those peaks. Now, you may be wondering, what are these little peaks all around the main ones? Okay, they're just the hydrogens being broken off. And at your stage, you don't care about those. Just care about the highest peak within the group. So care about that one, care about this one, care about this one. Don't care about any of the rest. And that's how you do a simple mass spectrum on a hydrocarbon. Okay, so we've looked at a simple mass spectrum. We're now going to look at a common type of question in an exam. So in an exam, the most important thing is that you identify the molecular ion. Okay, and often you'll take the molecular ion and then you'll compare it to empirical formula, and then you can work out what the overall molecular formula is. Okay, and they're the kind of questions that you get. The other type of question you can get is if you look at a mass spectrum like this, and we've already identified the molecular ion here. You can see nice little positive there. Okay, and here's our overall formula. Okay, and we'd get a mark for that. That's straight away. Just get a mark for that every time. And you can see the isotope peak right there. Okay, so there's the molecular ion, and there's your isotope peak. Okay, now this is for pentan-1-ol. We've drawn pentan-1-ol, and we're going to look at a question that was used before, but this can be used with different functional groups. There are a few different ones that can do this. You can have a functional group at position number 1, so this is position number 1, or you can have the functional group at position number 2 or 3. So sometimes you can tell the difference between these isomers with a mass spec, and they don't often ask you to analyse these peaks down here, but in this type of question they do. So we're going to show you what you need to look at. So, first of all, we do our molecular ion, we get our mark. So let's break one of the bonds. So remember, we don't break the carbon-hydrogens, we just break the carbon-carbons. Okay, and when we break the carbon-carbons, okay, you'll see it's coming. Okay, and there we go. You can see I've broken that carbon-carbon bond there. Okay, and then I just find out what this is and what this is. And remember, there can be two molecules going through. One will break to form this positive ion, and one will break to form this positive ion. And if they are, you count that, that's 31, okay? And then the other one, okay, down here is a relatively simple one that's always heard of, okay? And that's a 57, and you'll see it somewhere in here, but everything has 57, so we're not going to bother with that. Okay, so that's 31. You've got 31. You can see the 31 right here. So let's now look at pentan-2-ol and see whether it has 31. Okay, so let's look at pentan-2-ol. You can see pentan-2-ol here, and it's got 88, the molecular ion again, and we're going to break that bond. Okay, so we broke that bond, and we broke it where the OH was. Okay, if you break it where the OH was, you find that this bit is 45. Okay, and you'll find that the other bit is 43. So you've got the 43 here and the 45. But look, you don't have a 31, or if the 31 there, it's tiny. Okay, so that means that you can tell the difference. So I'm just going to quickly go back. Let's quickly go back. There's your 31. So you've got your 31 right here. And then I go forward. Okay, there's your 31. And then I go forward. Look, not there. Okay, which means that you can tell the difference between, let's just put all the colours in because I like the colours. Okay, you can tell the difference between pentan-2-ol and pentan-1-ol. And sometimes there's not many functional groups that can do this, but there's a couple. Okay, just break it next to where the functional group is, and then just see what peaks you get. And then you may be able to tell the difference using a mass spectrum. Okay, well, there will be a video in future on exam-style questions and mixing up IR and mixing up mass spectra, and we'll go through one of those, how you do the empirical formula and you do the molecular formula. But if you're not sure, have a look at the empirical formula video that we have done. And I hope this explains mass spectrometry well. And if you do like it, please share so as many people get as benefit as possible. Thank you very much.